Good.
All right, good morning. We've had the pleasure this semester of working alongside Hampton University and their architecture students with the neighborhood of Aberdeen Gardens. So projecting this neighborhood in the future, we want to plan for resilience against sea level rise and against increasing rainfall intensity that's causing some serious flooding there. So this whole semester has been about creating solutions and we've come together to do that. It's been a pleasure. So without further ado, the presentation's broken down. We're going to start going over the history of the neighborhood, and we'll roll into our work in the community and kind of what their thoughts were. And then our design and our preliminary research, and we split into three parts. First group being kit of parts, second group being roadway, and then creek remediation, and we'll finish off with a summary of everything.
So excuse me, my name is Austin Biter. I'm one of the team leads and the assistant project manager for this one. I'm going to start by diving into the area of interest and kind of give you a little bit of a background on the area that we're studying. This is the Aberdeen Gardens. Some of it takes part in the historic district and then a little bit outside that area as well. This is a sample map that we put together in GIS. There's around 14,000 residents that live in this area. There is an elementary school. They're a very involved community. They have a lot of community groups, such as the Historic and Civic Associations, Neighborhood Watch. They also have food banks and education programs. And they're very attuned to their own issues of flooding. And they're very excited to assist in helping out with those issues. I want to get into the history a little bit, just of the historic district and the surrounding areas. It was a neighborhood initiated by Hampton University, which was then the Hampton Institute. The completed project was done entirely by Black engineers, architects, and laborers. It was funded by Franklin D. Roosevelt and finished construction in 1938. This is an image of neighbors arriving around the time that people moved in. It was the second neighborhood in the nation built for the settlement of Black Americans in Virginia. And it has the History Museum within those bounds, the Tucker Family Cemetery. The Tucker family was the first African-American born in Virginia. The district is recognized with the National Register of Historic Places and the Virginia Landmark District. This is a showcasing of the Community Speaks. It came from one of the surveys that we conducted through Wetlands Watch. The main issue with Aberdeen Gardens is the flooding in the streets, yards, and occasionally the houses. The water can stand for 3 to 4 days after a heavy rain and has caused car damage to multiple families. Going through the existing conditions a little bit, we see that there is a very high amount of flooding. This photo was taken on November 12th, 2020. It just showcases how bad it is. We see it's like almost up to the tires of the car. This day, according to Weather Underground, showcased 1.16 inches of rainfall for the 24-hour period. Comparing with our calculations, it's a less than 2 years flooding event. These are some more images, one of a park and then another one of the same neighborhood. There is a lot of structures that exist already, but they're all very old. This data came from GIS from the city of Hampton shapefiles. There's a lot of curb drop inlets, linear pipe that's already installed, and numerous outfalls that go into Newmarket Creek as well as Aberdeen Creek. And looking at this image, we see Aberdeen Creek runs along the east side here. Newmarket Creek is on the west side. And then the entire area that we're looking at is just a little bit bigger than this, which we'll showcase when we look into the watershed areas. These are typical images of the curb drop inlets and yard inlets, which we can, or yard drains, which we can see are prone to getting sediment buildup, and they're prone to sediment buildup and need to be looked at a little bit more in terms of cleaning and stuff like that. These are an overview of some recent projects that we pulled our studies from. We had the Mary Peak Watershed Report and the Lake Shores Watershed Study. They're both a little older, but some of the things that they went through became relevant when we looked through our methodologies and when we looked through solutions that they proposed previously. They both went through XP Swim or PC Swim to do modeling, so we relied on their results to determine locations and the amount of flooding.
Right, so hi, I'm Tara Emma King. I did some of the historical research on the high water elevation. This was important because it was kind of under the umbrella of pre-existing conditions. So we started looking into the historical data from 2 points. We looked at Sewell's Point here in Norfolk, and then also the Newmarket at Mercury Boulevard out in Hampton. This was important because it correlated 2 data points and it helped us get a really good prediction of what water elevation could look like in the future. So collecting this historical data for the past 5 years showed us that we could graph the trends. As you can see here, we have some of the data that we put as raw data into Excel. One thing that had to be accounted for was Sewell's Point was measured in mean low water. So we had to add 1.61 feet to that to make it equal to the NAVD 88 on Newmarket. And here's the resulting graph. As you can see, the orange is Newmarket Creek and the blue line is the Sewell's. And you can see how they kind of ebb and flow as they're tabulated together. And this kind of relates coastal data with inland data. And it's important because Newmarket Creek, which feeds into Aberdeen Creek, also feeds into the ocean. So dependent on tide. So why is this important? Climate change is a big problem. Obviously, it causes sea level rise and an increased intensity of storm events. And this map shows just how large the watershed area is. And it shows how much an increase in water level can affect the residents.
Okay, so we chose to attack these issues from 3 different avenues. So we split into 3 groups. The first group is the kit of parts. So this is at the parcel level. So each individual lot, these are solutions that homeowners can implement at their level to reduce flooding and to slow and store rainwater and prevent it from overflowing the current systems. Next group was the group that I participated in, the street renovations. So we'll talk more, but the streets are currently graded back towards the houses. So we came up with some solutions to redo the streets and to store water and once again prevent excess water from rushing into the system. And the third group is regards to creek. So the actual creek itself that runs through the neighborhood that you saw earlier, our third group remediated that. And without further ado, we'll move into our first group, which is kit of parts.
Yeah, so I can take that. All right, so again, I was team lead Austin Bider for the kit of parts group. We're going to jump right into it. This is a brief introduction of ourselves and the roles that we had, which we'll again reiterate as we go through the presentation. What is kit of parts? It's a fantastic question that even I had because I'm not an architect, and apparently this is an architectural term. It's an idea that basically explains how you can come up with options or create a toolbox for a problem that you've been given. So what we did was we went through solutions that were given by the city of Hampton and the architecture students for how to fix flooding on residential properties. So we're trying to store and slow water from reaching the streets and the creek that would otherwise cause more of an issue. By doing so, there's less burden placed on the city, the road groups, the creek groups, and less runoff that could enter there in general. The important part is this offers choices because the aspect that we're coming from is that residents can put these on their own properties with their own construction and their own choices and materials and those kind of things. Recent efforts that were important involved, we decided that since there's a very vocal community with very strong historic values, we're specifically in the historic district was our area of focus. We want to preserve the architecture that's existing since it's very real from the 1930s. Not much has changed in that neighborhood other than some small additions. And we wanted the residents' desire to be involved to be honored. We wanted them to be actively participating in this project. Recent city efforts, and this is kind of the focus point of the kit of parts solution, because they had the RAIN program, which recently got pulled back, and they're supposedly revising and bringing back into the environment in the future. But the RAIN program stands for Resilient and Innovative Neighbor, and essentially all they're doing is they're going to reimburse residents for rain gardens and gutter improvements and different things they put on their properties up to $1,000. And they're going to inspect and make sure that it's maintained correctly after you build it. They also have programs for education along with the Chesapeake Bay Foundation. So then we go into our methodology. We went through investigations to understand the extent of the flooding and where it was happening. We used 311 call reports from the city that are collected, essentially saying that residents call in, they complain about flooding, how often, how bad, and where is it at? And then that's when we determine kind of where we would place some of our solutions. We looked at community input from Wetlands Watch and previous studies from the Hampton University of Architecture. And handing it off to Carlos.
So my name is Panagiotis Yarko. I was responsible for the soil survey and I did my part with Austin in the cost estimation. So in terms of soil conditions, everything we have was taken from the USDA NRCS soil survey. And as you can see here, we have 6 main land complexes, but we only focus on like 4 of them, which are the Mandan Urban, number 15 down south, which is 40% of our land approximately, it's 39.9 to be exact. Moving north, we have number 18 with Nemo Urban land complex. That's the biggest one and the most important one. This is 45% of our land complex. And then the other 2 ones, number 26, Urutan Dams and Urban Land, which is down south, 26 and 27. These are the only ones who are like residential. The rest of them are like small here, which is only like it's agricultural, so we don't work much with that. More in depth, we're more focused on two of them, number 15 and number 18, like I said before, Mandan Urban. This one is classified as soil B, which has a good infiltration rate. And this one consists of loamy and sandy sediments. Number 18 is Nemo Urban, and this one is soil D, which has a bad infiltration rate compared to soil B. And this one, again, is loamy and sandy. The only difference between them is that Nemo, number 18, up north has more coarse sediments, which is harder to work with, and it has worse infiltration rate. So this is the precipitation frequencies. These were taken from the NOAA Atlas 14 precipitation, especially for the Hampton roads and in the Virginia area. A very important thing about them, we got the precipitation frequencies for the 2-year rainstorm, the 10-year rainstorm, and 25-year rainstorm. A very important thing about it is that we had to add 20% to our values, to our regional values, because it was recommended by the city of the Virginia Beach and the Dewberry report because of the climate change. So we just added 20% extra to our original values because it is expected the flooding is going to get worse in the next coming years.
I'm Judge Steckline. I did a lot of the hydraulic calculations. So this is the risk analysis. This is a flood insurance rate map taken from the FEMA website. The blue area, this just shows a good representation of the problem areas and the flooding in the historic district. So the blue area is 100-year floodplain with a 1% annual chance of flooding. And the orange area is a 1 to 2% annual chance of flooding. So this really just shows Langston right down the middle, maybe east a little bit. That's where we got a lot of our complaints from, a lot of work that flooding is happening. There's a watershed delineation. We utilize Stream Stats, which is a tool on the USGS website to map out these areas. Watershed Area 1 on the west side, on the west side of the historic district is 217.6 acres. And then Watershed Area 2, which runs down the middle where Langston is 39.7 acres. We didn't do the east side because that's the creek side, so their whole team analyzed that section. Here's some of the calculation parameters. So we did the weighted curve number, which is basically just the potential stormwater runoff for each area. So Watershed Area 1 has a much higher curve number than Watershed Area 2. And then the time of concentration was calculated by taking the farthest point in each watershed area and then calculating the time it takes per hour or in hours to get to the point of analysis, which is Aberdeen Creek at the bottom. This is a summary of the watershed analysis. We use the SCS direct runoff method to get the runoff in inches. Runoff in inches is higher in Watershed Area 1 because those were calculated using the curve numbers, which it was higher for Watershed Area 1. And then the peak discharge method, we use the graphical peak discharge method for the peak discharge and cubic feet per second, much higher in Watershed Area 1 because it's a much larger area. These are the hydrographs and rainfall distribution. So once again, the Watershed Area 1 is much larger than Watershed Area 2 for rainfall distribution because of the curve numbers. And then this graph on the right, the hydrograph, shows the time to peak of each watershed area. So for Watershed Area 1, takes about 1.2 hours to peak, and then Watershed Area 2 is a little longer at 1.3. And these are the calculation parameters for the residential analysis. So for the residential analysis, we come up with 4 different scenarios based on the typical lot sizes and the typical soil conditions found in the historic district. So we did a 1/4 acre and 1/2 acre lots with B and B soils. And these are the CNs and the time of concentrations. These were taken straight from table 2.2 and the TR55 handbook. The CNs were, and then I calculated the TCs based on, I think the 1/4 acre was 150 feet, and then the 1/2 acre was 200 feet of sheet flow. And this is a summary of the stormwater analysis for the residential parcels. So shows the same thing as the watershed analysis, except I added the runoff volume just to show the sheer amount of volume coming from each scenario, each lot, and each soil condition. And these are the rainfall distributions for the 1/4 acre lot size. 1/4 acres has a larger peak or larger runoff than the 1/4 acre B. That's due to the worse soils and hydrologic soil group T. And this shows basically the same thing. It's hydrologic soil group D soils are always going to have worse runoff potential than hydrologic soil group D.
All right, so my name is Joey Wooten. I did some work with the Virginia runoff reduction method, quantifying our results for our recommendations and checking our compliance with nutrient removal. So with all the analysis done on our soil conditions and rainfall data, we can start moving on with solutions that residents can do. Now, our group specifically focused on what residential parcels can implement in their yards on homeowners on their land, what they can do. So our best management practice solutions are not going to improve the large area requirements like dry soils or anything like that. We're going to focus on smaller scale BMPs like rooftop disconnects, rain harvesting, micro bioretention, and we're going to throw in evapotranspiration just to talk about how planting native species of trees can make a difference and help residents feel good about what they're doing. So the first one we're going to talk about is rooftop disconnects. So a large portion of impervious area on residential parcels is the rooftop, and to manage the rainwater coming off of the roof, we recommend installing gutters. A lot of the homes in the historic district do not currently have gutters, but a lot of the newer ones do. So we were recommending the ones that do not have gutters to install the gutters. And this will be like the first step in managing the water coming off of the roof. So this is just a quick snip of the design criteria we used in the BMP clearinghouse for rooftop disconnects. And then, so coming off of the roof from the gutter, we can install a rain barrel for rainwater harvesting. Residents can add as many rain barrels as they please in their yard, and they can use this water for various purposes like watering a rain garden or other gardens. However, this just offers a way to store some of the rainwater before it gets to the street. And it will also retain the water for a certain amount of time, as the overflow will then sheet flow into another BMP before going into the watershed drainage area. So the BMP downstream of the gutters and the rain barrels would be a rain garden. Rain gardens offer volume reduction as well as water quality improvements from nutrient removal because of the native plant species. So the overflow of the rain barrel and also directly coming from any gutters that are not connected to a rain barrel will flow into a rain garden. And next slide. This is some of the design criteria for what rain gardens, the rain gardens we're suggesting on level 1. And this is what we use for the design of that. And to throw in evapotranspiration, which is the way that native plant species can be utilized to store and improve the water quality before getting to the Chesapeake Bay. We want to throw in that this is not yet quantified as a best management practice. It's not listed on the BMP clearinghouse. However, with strategic placement of native plant species and picking the right species, it will make a difference. So next slide. So these are some of the plants that homeowners may choose to put in their yards. We have the bald cypress, black chokeberry, and purple coneflower, all listed as native plant species that can be utilized in the area.
And these are the recommendations that we came up with. So we have a half-acre lot, which is a duplex style home, which you find a lot of those in the historic district, and then the quarter-acre parcel. So what we decided to do was add gutters for homes that don't have them, like Joey was saying. The gutter would be directly outfall into a rain barrel, which would sheet flow once full into the rain garden, which is downstream. Depending on the grading of the house, it might be placed in a different area. I just thought that it would be a lot better to have a visual to see what we're talking about. So specification, the 50 square foot rain garden is sized based on 5% of the 1,000 square feet of impervious area, which is the roof. And then the rain barrel, I think we did 55-gallon rain barrels, and the cost estimate, which depending on the homeowner, you can get more rain barrel, you can store more water, just depends on how much money this homeowner wants to spend. And then the placement. So depending on the water table and the soil conditions, you can do a rain garden in the B soils. It would work a lot better than trying to put in the D soils because the water table is a lot higher. So for the D soils, it might be better to do a raised rain garden with a outfall directly to that. And which is fortunate because the HSGB soils are in that that southern portion of the historic district, which is where a lot of the problem areas are occurring, just because of the sheer volume of water that's coming from the other side of the watershed.
And talking about quantifying the results of our proposed recommendation, we came up with 3 case scenarios of varying levels of participation with about 500 parcels, residential parcels. We calculated using our results from the Virginia runoff reduction method. We calculated the runoff reduction and phosphorus removal from each lot based on the quarter-acre or half-acre lots. And we calculated how much of an impact 25% participation would have, 50% and 75%. And this scales linearly because each lot will, with our recommendations, will remove about the same amount of runoff and phosphorus. So higher accessibility to our solutions will lead to higher participation, and higher participation will lead to better runoff reduction and water quality improvement.
So this is the cost estimation. Everything here, all the prices here, were taken from the building construction manual of the RS Means 2022 edition. So everything here is very accurately up to date and with inflation. We have in detail here every single material with the quantity, the unit price and cost and total cost. And as you can see, the final price is $15,000, almost $16,000. And this is very unfortunate. And there is a reason why this is so expensive. There are 3 main reasons. First of all, it's COVID. After COVID, all the prices skyrocketed, so everything is very expensive. Like for example, the gutters are very, very expensive right now on the market. And moving on to the second reason, we added the ENS, erosion and sediment control, for each parcel, but that's not necessary. That's only for the parcels that have their sediments drain in the creeks. So let's say for a parcel that is far from the creek, we don't need that because it won't drain there. And the last reason is because we added labor and construction costs. So if any resident want to like build it themselves, it's gonna be a lot cheaper. And like Joy said before, gutters, some houses have gutters, some houses don't have gutters. So this is like the most expensive scenario possible. 60,000 is like the most expensive scenario. That's for the houses who don't have anything. Of course, there are some houses who have rain barrels or like rain gardens. And like Austin said also before, the city is reimbursing $1,000. And that was 10 years ago. So now I'm assuming after COVID and with the inflation, if they consider all these, they will do something more than that. Yeah, so that's why it's so expensive.
So to close this out,
We're both here struggling. What was the total number? We can't read it.
$15,720.
16.
$15,720. To close out the kit of parts portion, I just wanted to showcase some of the design iterations. Originally, we were going to have students from the architecture class showcase these, but they were not able to attend today. So my analysis will not be as technical as these, but they showcase how the rainfall would come off the top through the gutters, which they had not yet put in, and then into the rain barrels and then the rain gardens. They showcase this during the day and at night to kind of show how the community could become involved, how they could have a nice place for barbecues and other community gatherings in the backyards. We could even do orchards in the back with the large style trees, since there's a lot of area in the backyards of these homes. With this, the Kit of Parts group has put together solutions that will help flooding slow and store it on people's properties before it reaches the next group, the roadways.
Good morning. My name is Catherine Marco, and I'm one of the members of the roadway group. I want to thank all of you for coming here today to view our presentation. Thank you. Yeah, everybody in my group will introduce themselves as their slides come up. These are the Hampton University students that helped us with our design. Unfortunately, they were not able to be here today. So the executive summary of our project is we are proposing regrading the roads to slope towards the medians instead of towards the curves, which they're currently doing. We're also proposing to have dry swales on both sides of the median to hold the water instead of overburdening the existing stormwater lines. The reason that we chose the roadway is because there are complaints about excessive rainfall staying on the streets. And our scope of work is we are focusing on the roadways that have medians only because they do not have stormwater lines currently. And then when we went out to the area to scope, we determined 11 different median locations, as you can see here. And so this is a typical roadway that we did. And what we would do is we went out to the field to get the width of each road as well as the width of each median. We also took inventory of the number of power poles and trees that are in the medians. Weaver Road is kind of an exception to the roads, and the reason why is because there is a signal here, and also it is the road that is closest to the elementary school. So overall, the roadway conditions, the roads are very wide to allow traffic flow in the area. Also, there is a lot of street parking that happens. The roads are in good condition, and as we said earlier, the roads slope towards the curves instead of the medians. Existing flooding conditions, rainwater currently sits in the curves after rainfall events. The rainwater also pools around the medians instead of infiltrating. And the rainwater also backs up on the existing system to the creek.
Hello, everyone. My name is Zahim McCall. I'm going to be talking about the constraints and the pavement design for the roadway group. So this image was taken by the National Web Soil Survey, which contains data on water table elevation. If you look at this upper red portion containing Weaver Road as a water table elevation of 6 inches. And as we move further down, going towards New Market Creek, for most of this yellow region, we have a water table elevation of 2 feet. Like Catherine said, we did an initial site visit where we observed and recorded over 146 trees and over 37 power poles located in the median. Since this is such a substantial amount of natural life and utilities, our approach is to disrupt existing infrastructure as little as possible. Our initial site visit also we've seen that the roads widths range from 18 to 25 feet and the medians range from 16 to 20 feet. This image was taken from Hampton GIS. If you look here, you can see this green line, which indicates a sewer line running directly underneath most of the medians in our scope. We have a clearance of 8.5 feet, so that would need to be considered when any digging is taking place in the median. This also is taken from GIS. This blue line indicates a stormwater line, which runs perpendicular from most of the medians in our scope. We also want to make note that for our initial site visit, we did not see any curb inlets or storm drains present throughout the medians. Also, we have a minimum clearance of 2 feet between the roadway surface and the stormwater lines. So that was considered when we did our design process.
All right, my name is Jonathan Savage. I know I've spoken previously, but I formally introduced myself. So with our work, it was kind of broken down into 2 sections. So part 1 being the roadway itself, and then part B being the retention device. And that's where my work was focused. I focused on designing something that was gonna hold water, once it regrades and drains from the street. What happens next? So in our approach, there were a few things that we considered, going through when thinking about initial designs. The first thing we wanted to do was, like they said, there was a ton of existing trees and power lines, which would just add cost. And we didn't want to, demo mature trees that were healthy. So we wanted to disrupt existing infrastructure as little as possible. It was also mentioned the lane width. We wanted to maintain that because through site visits, we saw that a lot of the residents park on the streets. So we didn't want to overcrowd the roads and make them narrow, because that was gonna disrupt the current function of kind of the neighborhood and how they operate. Next, we had an unusually high water table throughout, so we were a bit limited in what we could do, because in some places, especially seasonal highs, the water table could be as high as a foot beneath the surface. So that was something else we considered. And then the existing stormwater infrastructure. So especially when it rains, the creek has a tendency to get really high and the existing stormwater lines back up. So the water is like spilling out onto the streets from the existing lines. So we didn't want to overflow that and pour even more into it. So our focus kind of shifted towards retention rather than redirecting that water. And then lastly, we wanted something that was going to be sustainable. So it was mentioned earlier, the projections for sea level rise and then increasing rainfall intensity. So we wanted to make a solution that was going to hold up as time passes. So this is an example of our first design. So it's a French drain system essentially. So once again, the roadways are going to be sloped now towards the medians. And along the median, we had the idea of making sort of a French drain, which was sloped to a central point to where it would then tie into the existing line beneath. This schematic kind of shows exactly what that looks like. The reason we ended up shifting from this and moving along is because, like I mentioned, what this actually would do is it would accelerate the water going into the existing line, and it would just cause more water to rush to the creek, which is opposite of what we needed. So we moved on from this design, which led us to a couple of other ideas. Next, we discussed the use of permeable pavement. So essentially, it's like pavers along the street, and this would allow water to seep directly through the street. However, according to VDOT, permeable pavement isn't permissible for high traffic areas. So you see a lot of times in parking lots, but for a roadway that has traffic, it's unsafe. So we were forced to exit that design as well. And then we considered using a wet swale. So a wet swale is great in areas, especially with a high water table, because it allows water to stay in it and it'll retain and levels will vary. However, being that our application is so close to the homes, one issue that would be present with the wet swale is mosquitoes. So here in the south, in Hampton in the summertime, sitting water is going to attract mosquitoes, and that's not safe for residents. So that led us to our final design, which was a dry swale. So here, these are some of the calculations we used for our dry swale design. Essentially what the dry swale is, it requires excavation along the ditch. So there'll be one of these dry swales on each side of the median, and the road will be sloped to this dry swale. We have to excavate the entire ditch. But there's 3 layers. So there's a layer with a really coarse gravel sump. And then above that, there's a smaller layer of pea gravel, which is then covered by a 2-foot section of engineered soil mix. So this engineered soil mix is going to be a sandy mix that is highly impenetrable. And it's going to provide the capacity we need to store water and then let it infiltrate as time goes. So here at the bottom here, the widths, so we designed for the worst case and typical through, which was Langston. And typical throughout all of our medians, we use a 3-foot width for this dry swale. But we do have noted that on Weaver, which is a special case where there's a turn lane because it goes to a major intersection with a traffic light, it's a little bit more area. So in this particular design, the width is 4 feet. Here is a drawing provided by the Hampton University architects, which shows exactly what I just talked about. You see here, this is our dry swale. You can see the 3 layers, the gravel sump, the pea gravel, and then the engineered mix on top. And then this is a replication of the roadway slope. So you'll see the roads will be sloped to the median where the water will then go into our ditch. Oh, sorry.
Right, I'm Catherine Marco again. So I did the traffic volume calculations in the area because we had to get the AADT for the streets to design our pavement. So VDOT does not have AADTs available for residential streets. So we had to estimate the traffic in the area. And so I did this by using the ITE Trip Generation 11th edition. And I did 158 single family homes. And then Aberdeen Elementary School has 443 students. So that's how we came up with this number. I got the AM peak, PM peak, but most importantly, got the daily traffic in the neighborhood as 2,496. From that, estimated the volume per individual street. And as mentioned earlier, Weaver Road will be receiving the most traffic because there is a light there and it is also closest to the elementary school. So I came up with an AADT of about 574 per day.
So for our pavement design, we use VDOT's geometric design standards. The main takeaway for this is, since we're dealing with residential streets, with speed limits of like 25 miles per hour, we have to have a 2-1 slope when we regrade them. We use VDOT's pavement design guide for subdivision and secondary streets. Our present day volume, like Catherine just stated, we use peak volume for Weaver Road, which was 574. And then we use a growth rate of an estimated 5% based on historical traffic data. Finally, our final design volume was projected for the next 10 years. We use a story support value of 27 for Hampton, Virginia, and then use our final design volume of 234 per lane. Using this, we were able to find our required thickness index of 7.2. Now that we have our required thickness, we were able to choose materials to satisfy those requirements. As you can see, we have different kinds of concrete for our surface, intermediate, and base layers, followed by 7 inches of cement treated aggregates for our sub-base and 6 inches of gravel for our subgrade. Since our calculated thickness index was 25.43, which exceeds our required thickness, our math checks out.
So after we got the required thickness, we were able to do the slope calculations. We did it for each street. And we did a slope of 2% per VDOT standards. And so we did thickness additions for each street. And these will be the new roadway profiles. If a street had the same width, then it would have the same measurements on both sides.
These are a list of the permits that we need to start construction. First, we have to submit permit documents to the city of Hampton to obtain a building permit. Once that's approved, we need a land disturbing permit, Virginia Stormwater Management by Virginia DEQ, erosion and sediment permit, right-of-way and demolition permit. And then lastly, we need a stormwater pollution prevention plan to be submitted to the contractor for the duration of construction.
So for the construction schedule, we had it split up into about 3 different parts. The first part is just the planning and design phase. The second part is one side of the median, and then the third part is the other side of the median. We specifically split it up so that one side was done at a time because people need to be able to access their homes and have parking during that time. The estimated completion time for this project is about 6 months. So next is the cost estimate. And it's kind of divided into 4 parts. We've got the roadway regrading, the dry swale. We also have traffic control and erosion measures and miscellaneous. So in the miscellaneous costs, we made sure to add a 30% contingency fee. We also did engineering fees, architect fees, overhead and profit, as well as a lump sum for surveying costs. We used the RS means data, but most of our cost estimating actually came from VDOT district averages. We also had to get a direct quote from one company for the engineering soil mix because we could not find it in any of the VDOT data or the RS means data. So the rounded total cost estimate for this project is about $1.8 million.
Yep. Right, so hi again, I'm Tara Anna King, and I'm joined by my group members, both Madeline's and Vinan. We were part of the Creek Remedial Group. We were the third and final design group of this project, and we focused on tackling one of the major point sources of the water on Aberdeen Creek. These are two Hampton University architects. They couldn't join us today, but they helped us with some schematic designs and other things you'll see throughout. So we split our design goals into 3 major goals. And throughout the next few slides, you'll see how we tackled reducing property flooding first and foremost, addressing the community's desires, and restoring the creek integrity and aesthetics. So a brief overview of how we tackled those things. We started with a footpath from Aberdeen Elementary School to East Weaver Road, and Madeline will talk a little bit about that. Creek cleanup intervention to reduce the litter and the stream blockages that were causing the stream to remain stagnant. Erosion armor to support the areas of need along the creek bank that were eroding from the water. Introducing vegetation, permeable pavement, and a constructed wetland as well.
You just keep. My name is Madeline Wilson. There are 2 Madelines, so I'm Wilson. I mainly did the designs for the addressing community desires, and I also led the designs for multiple BMPs, which you'll see later, which helped mitigate flooding in the area. And then I did the cost analysis at the end. So first, I'd like to start with what was brought to us by the Hampton architects, which the idea presented was to design a trail from Aberdeen Elementary School down to the historically significant cemetery, Tucker Family Cemetery in the corner there. And this idea was supported by a group called Resilient Hampton, which had done a nearby and similar project called Big Bethel Blueway, seen here. The idea that they wanted was to connect multiple communities with water walks throughout various local waterways. However, on our research, we discovered that the property lines go directly up to the waterfront, and that you'd have to destroy a lot of large existing vegetation that was already helping mitigate flooding, and you would possibly disrupt an already eroding creek bank in order to make this happen. So after considering the large construction to be difficult, disruptive, and very costly, we tried moving on to something else. So instead, we worked with the Hampton architects to design just a school trail. This school trail will reinforce and extend an already existing desired path. And that desired path goes, as seen here, it goes from Weaver Road up to the elementary school. The path is going to be about 2,100 feet long. It'll be a comfortable 5 feet wide, and it'll be made with reinforced permeable gravel. That's the end of the center. It'll come to a total cost of about $40,000. Then we also wanted to take some action regarding the existing creek litter. These images were taken on site by us just during our site walk. So you can see that it's a combination of debris and small trash that is clogging and contaminating and just making it very unsightly. So we looked into a way to renovate that. We discovered that Hampton Community Development and Hampton Clean City Commission work together to evaluate the Hampton Community Development evaluates the creek, and then Hampton Clean City Commission provides equipment and guides the cleaning process. We also found that Aberdeen Elementary School could be a candidate for not only a one-time cleaning, but also a program such as the Adopt a Spot. And they had previously been involved in such a program, but they haven't been active for years. So reinstating that would be simple enough, and it would be a good engagement for the elementary students. So another way, besides reinstating a volunteer cleanup program, would be to put in a trash collector. We strategically looked at where to place a trash collector and decided that at Aberdeen Elementary School would make the most sense because it would collect the debris and litter that was coming off of the parking lots and roadways that are upstream that feed directly into this through the storm drains. That seemed to be the largest source of the litter. So considering the size of the creek and the expected debris, a litter trap type of trash collector is what was recommended. This is pictures of a litter trap. It's essentially a floating cage that just collects trash and debris and does require low maintenance. A similar creek in Asheville, North Carolina, is one where an Eagle Scout had designed such a litter trap called the Trash Chout Junior. This type of design is what works best for our size of creek. So we could purchase a full package plan from this. It's the same design, and this would include the build cost and the consulting services for placing it. And then this would also include the consulting services would address the maintenance as well, considering it could be funded through sponsorship, and the whole package would be roughly $4,000.
Okay, so again, I'm Tara Enneking. I worked on some research regarding restoring the creek's integrity. So at first, dredging looks like a very promising candidate. The reason I say at first is because we quickly realized that dredging would not be an option as it's prohibited in tidal zones. Section 404 of the Clean Water Act protects the region we were looking at. And it means we can't do any sort of dredging in the region, which turned out to be a good thing because we realized that dredging would actually cause the flow of the creek to be too quick, and it would sort of push the flooding issue just to another zip code. Back to the creek itself, the creek has naturally occurring weirs, which means the water naturally pools as it flows. This actually helps to mitigate the flooding, and we didn't want to disturb the natural pooling, so it was a good thing that the dredging was not an option. An option, though, for us was soft armor reinforcement. This is a method that is used in a variety of ways. Vegetated riprap or joint planting is a really effective form of brush layering. And one of these methods is actually called live staking, which I'll explain later. It involves live cuttings of rootable plant, and these roots actually infiltrate the soil and help to root it more deeply and limit erosion. You can see that in this image here. Hard armor reinforcement was another thing I looked into. As you can see, it involves a lot of scouring of the soil, and it's a very invasive process. This proved to be an issue as the creek runs through people's backyards, and no one wants this sort of construction in their backyard. It's also very costly, and it takes a lot more time to implement as opposed to soft armor. And as said before, it could cause the flow to be too strong in the creek, which we do not want. Thus, soft armor is definitely preferred. It can include many methods, but what I looked into was erosion control blankets, turf reinforcement mats, and geogrids filled with soil. These flexible green techniques can be installed with little difficulty, and they're pretty easy to maintain as opposed to hand. So again, some options that I looked into, you can see here the product names. These are all available for purchase online. They're slightly more expensive after COVID, but they were all included in our cost estimates. And now we get into the vegetation. The bank existing conditions, as you can see from our initial site visit, there's a lot of erosion and there's a very steep steep sloping bank, which is not good. This means that the erosion is happening quickly and will only continue to happen. There's also a lot of foliage from the leaves we visited after the fall, obviously, and there's a lot of stagnant water. So after our initial site visit, we were able to see what we were dealing with. We were able to research native plants to Aberdeen Creek that we could implement to help with the erosion. We used information and research from the Virginia Department of Conservation and Recreation and the Virginia Native Plant Society. And we came up with these requirements based on our region. And with those requirements, we went through and physically highlighted what would work for our region. And we came up with these herbs, ferns, grasses, sedges, rushes, and shrubs and small trees for the region. These plants were handpicked as they flourish in stream valleys, and they do well in beds with medium to low sun exposure, which is what we're doing. And this was our planting strategy. I made this quick little mock-up. So as you can see closer to the water, we're going to clear the brush for more even water flow. And then we'll start with the sedges and rushes towards where the water table touches the ground. And then moving up, we'll go to the cattails, grasses, shrubs, and then the live staking of the weeping willows will occur. This will introduce native plants, and it'll establish soil root systems, as I said earlier, for increased stabilization. And this is just a brief explanation of kind of what live staking will look like. One of our Hampton architects made this image to show just where the live staking would take place. The spacing of the stakes would be 2 to 3 feet apart, and this was important because it helped us determine in our cost estimate how many willow bundles will we need to purchase. And then the roots would extend to dry season water, actually.
My name is Brian Connor. I helped a lot with the stormwater calculations. And so, yeah, so we had such a large scope of area. It's a very large watershed. It's about 1.8 square miles. And so it took us a lot of like trial and error to figure out, what type of BMP we wanted to do, the location of the BMPs. And so what we got here is the entire watershed, basically, and the flow path for our time of concentration calculations. And the flow paths were segmented, basically, and we took the average hydraulic radius for each segments. So, and the hydraulic radius largely affects the velocity of the channel, and as well as the slope. And the slope change was only about 20 feet from the start of the from the top of the watershed to the outlet. It was only about 20 feet elevation. So the slope's very very small change, and only made the velocities probably about 3 or 4, maybe 2 feet per second. So pretty slow flow. And this map on the left here is how you can subdivide the entire watershed into sub watersheds, and you can get the CN numbers for each. The CN numbers, like Kid Forrest talked about, or just land uses, and the soil groups reflect all those. And that map is actually made by one of our Hampton University colleagues on AutoCAD. Yep, and with the help of StreamStats, Hampton City, and one of the documents I'll show you next. And this is the document by Parsons Brickenoff, and they went through and they got profiles of all the way down from the channel into the Aberdeen Creek. And these are some of the profiles examples. This is actually a picture of right here on Weaver Road. It shows what the profile kind of looks like. These are all based off elevations, so we kind of had to manipulate those to achieve hydraulic radiuses or radii. And these are the Manning numbers we use for different segments. They've got quite a few different Manning numbers included in our calculations. And the methodologies, were the SCS, CN direct runoff, TR55 time concentration, and the graphical peak discharge method. All were included in our calculations, and the precipitation rates and intensities from the NOA LS14 were increased by 20% in contention with Virginia Beach And this last graph here is basically just a like a time duration graph. Basically shows the interval depths of the storm as they as it goes on. You know, it's at its peak at about halfway through the storm. And it's just like a durational rainfall graph for the city of Hampton. And let's see. So here are our theoretical hydrographs for Aberdeen Creek and for our suggested BMP areas using the SCS unit hydrograph method. Let's see, so and these are all 1 hour time based based on a 2-year storm. And let's see. Yeah, the flow rates are much smaller for these smaller watersheds. You know, as you can tell, the flow rate or the flows or the peak discharge here is on this graph is much larger for an entire watershed. Let's see, and these are some of our watershed summary, runoff peak discharges for our different areas. You can see here, and I kind of wanted to explain what the time base means. The time base is equal to the duration of unit excess rainfall. So use a 1 hour time base. So the rainfall probably only gets about 1 hour here, and this difference here is pretty much our time of concentration. And as the soil capacity decreases at the peak, it becomes equal to the intensity of the rainfall. And this is all and all converted to direct runoff. So this hydrograph basically shows like just the direct runoff. And you can integrate that, with respect to time to get the actual runoff volume. So this whole graph here will show the entire runoff volume for the whole watershed of Aberdeen Creek. And as you can see here, the peak discharge for just a 2-year storm for the entire watershed is about 7,000 cubic feet per second, this is actually post cleanup too. So this is when there's no trash. And so yeah, it's kind of and that's at the entering Newmarket Creek during a 2-hour rainstorm or 2-year rainstorm with a 1 hour time base. And that's about it.
Knowing the watershed and the extensive runoff volume, we considered BMPs for flood control. Our main focus was to slow and store the water because we thought that was most appropriate with the given constraints and issues. So we searched for a location to put a BMP, and originally we had looked closer to Newmarket Creek, as shown in the green circle in both of these. The point was to put it at the edge of the community, and this location in particular had a higher elevation. However, as you can see, this is from Hampton GIS. During a storm surge event, the area easily floods. And in this other image that shows from NOAA 2017 scenario, by 2040, this area is almost entirely underwater due to sea level rise. So when we looked for a better location, we looked upstream and before the creek starts to try to intercept the water before it gets there. So now, our original design was to put in a bioretention prior to the creek and intercept the water. We evaluated the existing infrastructure, and within the watershed, we found that there was a large parking lot that was contributing a lot to the runoff volume. So this is drone footage that we took over Aberdeen Creek. And this corner right here is the parking lot corner that we pinpointed as where best to put a bioretention. So we using GIS. Okay. Using GIS, we delineated okay. Well, we delineated the water runoff to that spot, not shown in the image. And then So when designing, there were some restrictions to consider. We are in the coastal region, so there needs to be a 12-inch separation between the bottom of the BMP and the top of the water table. And at this location, that meant the bioretention could not exceed 3.9 feet. So to accommodate, we used the minimum depth requirements for the surface drain, the soil media, and the gravel shown here. And that would total about 3.5 feet. So it would make it. However, knowing the contributing drainage area, we calculated the needed surface area for the bioretention, and that came out to 36,000 square feet, which far exceeded our available 10,000 square feet. We thought about expanding the area to meet this requirement. However, it is not recommended to have a single bioretention unit accounting for more than 5 acres of drainage area. And we had currently up to 15 acres of drainage area to this one spot. So we had to completely reevaluate and choose a different BMP more suited for the restrictions that we found, the constraints. So we turned to permeable pavement. The major issue was in this area was, of course, the large impervious surface area. So this felt appropriate for the high runoff volume. Permeable pavement is known to reduce the annual runoff volume by as much as 45%. And so we found the contributing drainage area to be 11.8 acres, and the total permeable pavement that we could put in would be 3.2 acres. So our design is to use porous asphalt, and we felt that this was, we chose this material because parking lots, it is a parking lot with businesses that would hope for the construction time to be as little as possible. And this material will last up to 20 years, would only have a 24-hour cure, and can handle all traffic loads. Our design, it works with accordance to VDOT as well as BMP Clearinghouse, and the pavement thickness would be 3 inches, the bedding layer would be 2 inches, the reservoir layer would be 11 inches, and we would include an under drain. Then the total treatment volume, considering the area, would be as much as 11,000 cubic feet, and the cost would be just over $1 million.
Okay, so I'm the last person to talk. I'm Madeline Atkinson, the other Madeline. So the next location that we looked at upstream was Aberdeen Elementary School. As seen here, the entire lot is around 18 acres. 2 other BMPs that we considered were bioretention. However, the drainage area feeding to the elementary school was much greater than 2 acres. And then we also considered a wet soil, which only can serve a maximum of 6 inches, which we were already greater than that. And look again. Here is the school, and then back there is a ditch where I will talk about in a later.
It has to finish. It's not.
Okay. So one thing we considered was a green roof. Initially, we had considered this entire blue area here, but then come to find out that the side slope there was much greater than 1 to 2%, which is ideal for green roofs. So we switched and went to this red area here, which is a pedestrian cover and is much flatter. We decided to go with an extensive vegetative roof, which is 4 to 6 inches, which is the smallest depth that you can have. We went with a level 1 design, and then the types of plants that would be added, since we're in the Chesapeake watershed, would be plants considered plant hardiness zone 7, and then different variations are listed there. And then this is where I calculated the treatment volume, which is based off the roof area, which is 467 feet cubed. And then with a media depth of 4 inches, we can store 400 feet cubed of that. And then since we were able to consider the entire roof for a green roof, we looked to doing cisterns, which accounted for the additional 21,000 feet cubed for the roof. There were a total of 4 gutters from the front face of the school building. So we are recommending 4 500-gallon cisterns at the front. And then the use can be used for irrigation and other uses. And the 2,000 gallons will account for a majority of the 200-year volume. The additional volume will be overflow, but it will help mitigate flooding. And so then this is the ditch I pointed out earlier. This is the delineated watershed for that, and the drainage area is around 24 acres. This blue area here is soil type B, and then the soil type over the ditch is soil type D, and the depth of the water table is 6 inches. Soil type D is ideal for what I'm recommending, constructed wetlands, because it is not impervious soil. Constructed wetlands are used to treat phosphorus and nitrogen and just kind of use as more storage, which constructed wetlands don't help with annual runoff reduction, but they do help with flood mitigation through, they have 4 bays at the face of them, which helps store water. So our treatment volume for the 24 acres was around 38,000 feet cubed. And then the extended detention with the size constraint of the elementary school property, and then the given depth from BMP Clearinghouse, I was able to get an extended detention of 700 feet cubed. So the side slope needed is 14 degrees, and then sizing for the remainder of the treatment volume, I had a length of 480 feet, which is the length of the ditch, and then the width was 45 feet and a depth of 1.75 feet, giving me a surface area of 1/2 acre. And then the BMP Clearinghouse also listed plants. So I picked a couple for the perimeter, emergent, and submergent. The emergent plants, there needs to be 4 aggressive colonizers so that the BMP can be fully colonized with plants, and it usually takes about 3 years. And so this is just a summary of some codes and permits and standards from BMP Clearinghouse that I was able to find for each of our different BMPs.
And then I did the cost analysis at the end. So in our final cost, we did include a 30% design contingency, a 10% architectural and engineering fee, and a 10% profit. So and we also did account for the location factor. We decided to do each cost separately because they're not dependent on each other. So the school trail is about $40,000 and will take about 5 days of construction. The green roof is roughly 10 days of construction, 156,000. The trash collector is approximately a flat fee of 4,000. The soft armor reinforcement and live staking for the entire creek is 144,000 and will take roughly 93 days. And then the permeable pavement will cost just over $1 million and be about 129 days. In addition, the constructed wetlands, we got a rough estimate of 51,000 and about 13 days of construction. And then the cisterns will cost about 5,000 and will only need a day for installment.
So we saw the pictures earlier. We saw water up to a car door. These are real problems. And with climate change and sea level rise, we don't think we'd be ignorant to get up here and think that our solutions can solve the world's crisis. But we genuinely believe, and we can say confidently, that with the parcel renovation, with the regrading and the drainage in the street, and with the creek remediation, we think that it'll have enough impact to positively influence the day-to-day life of the folks that live in Aberdeen Gardens. So with that, we thank you all. Once again, these are our 3 approaches, and we really think that it will have an impact that the residents will feel. So at this point, we'd like to open it up for questions.
This is Scott Smith from City of Hampton. thank you for your presentation. I thought you guys did very well going through the evaluation process and coming up with solutions. And I think the important thing is that there's no silver bullet to address the flooding, that we just don't have the land to create the one big BMP to solve everything. Going through some of your solutions, the one thing I agree with the trash trout or some kind of concept similar to that. The question would be access for maintenance. So once you collect all the materials in that device, how do you empty it? So thinking through the operational standpoint for that, when you're looking at the plantings along that outfall ditch or the Aberdeen Creek, think about salt tolerance of plants, since it is a portion of it's tidally influenced, so you'll have to have salt tolerant planting. And then for the trail width, I would recommend making that at least 8 foot wide, so 2 people can walk side by side. The 5 foot is even though that's a normal sidewalk, 2 people have problems walking side by side, and most of for trails and that we're going to an 8 foot minimum. So if you could incorporate an 8 foot trail, I think that would be better. But overall, I'm very impressed with your analysis and your recommendations.
Thank you, Scott.
Thank you.
I had a question for the green roof folks. Did you take a look at the existing roof and whether it would have like the structural integrity to work an intervention like that?
I mean, yeah, like we definitely considered the structural integrity, but there was a lot of in-depth analysis that we would have to do into that, and we didn't have access to that information about the school. It's an already existing building. If we were to make the building ourselves, perhaps we could design it to be just right.
Yeah, I think with all your recommendations, and that is a good point about the suitability, if it has the structural integrity to put the additional weight up on the roof. But I think the next step here that you've come up with conceptual design. So the next phase would be moving through a feasibility design where you would further investigate all these practices. There's additional investigation that would be required. So from a conceptual standpoint, I think that you're on target with it, and that yes, for a lot of these, there'll be additional investigations that will be required.
Any other questions?
Yes, it looks like the site is quite far away from the shoreline, right? Is it affected by level-wise?
Yeah, it is. It's actually still in the tidal zone. It is right on the edge, but the creek
Is classified as a tidal influenced waterway.
So the flooding is still affected by some stuff.
Yes.
and sea level rise.
So in your analysis, you only looked at the flooding caused by
We did consider, I think that was part of the calculation was an increase in.
Yeah, I don't think much a dynamic model where there's water that's going back and out, so that's just, yeah, those are our heads, I think, and that, I mean, but the fact, yeah, you're right, the water does, there is a storm surge effect.
And I do think, in addition, the creek we talked about, it's like natural cooling years. So there is a little bit of natural protection from a storm surge all the way up the creek. So just at Newmarket Creek, which is sort of at the very edge of the community in the start, that's where you'd experience the most amount of storm surges, which is why we moved the BMP.
So you looked at the different two different devices. Yes. Which device did you use? Will be done.
2 years. Is that?
Treatment volume for from BMP clearinghouse is based off a 1-inch rainfall event. So anything above that, certain BMPs can't collect. So like the green roof and cisterns, they only have like a certain capacity based off a 1-inch storm event.
What is that based on? Which return period is that?
And it's just the 1-inch. It's just based in the calculation. It's just a
Right.
part of the calculation.
Corresponding to a 10-year event, year event.
Yeah, I think it just corresponds to like a 1-inch rainfall, so the different events, it could be like 3 inches, 4 inches, 5 inches for 10 years, 25 years. I just did the BNP clearinghouse, just kind of does it based off just like a 1-inch rainfall. So it's not really based off of like events like for that area. Yeah, it doesn't really help, in the treatment volume for a 1-inch rainfall when you've got, events that are 3 inches, 4 inches, 5 inches. It only really helps like a fraction of what 2-year storm would help or actually would do. So yes, but I mean, that's just kind of how they size up treatment volumes. It's based off a 1-inch rainfall.
So you have to have multiple solutions to catching event. But I didn't see any discussion on that. It looks like you get different solutions, but they were not considered together. For example, you get that water retention pond. You don't have enough space, so
Yeah,
we don't do that, but then we go with permeable pavement. How about we go with a smaller retention pond and permeable pavement?
we did actually look into combining
Okay.
BMPs, and they didn't
With
work
the
out.
high water table and like soil conditions and just most of the area already being developed, there were a lot of constraints that eliminated a majority of the BMPs. So the ones we've suggested are the ones that fit the criteria of our area.
We had really hoped that doing the permeable pavement would handle enough of the water that we could put the bioretention there. And I suppose technically you could, but it's just not recommended for a single bioretention unit. Theoretically, you could put in more than one, but you'd have to really look into the placement of those. It didn't necessarily make sense for the areas that we were.
I just want to add, it's such a huge area, and you really couldn't decide which BMP or what type of BMP you use. I mean, it wasn't like you're assigned like an area and a certain BMP, design this, we just had like very ambiguous. We kind of had to spend a lot of time deciding on what to do and where to put it. And that's, kind of what just happened to me this semester about.
Looks like permeable pavements is the easiest solution because there's already pavements. Just replace pavement. By retention pond, you have to designate the space, which may not be feasible. So, if I may, I go to another question. So, talked a lot about the costs, but you didn't talk about benefits. So any solution that goes in needs to be just justified. Right? So, for example, you propose a $160,000 flood mitigation strategy for this neighborhood. What is the benefit? That's why the city or whoever wants to, go for grants to implement such things will be required to have. So, did you look into benefits at all?
Well, I can tell you, when we went on our initial site visit, we spoke with a woman who had recently redone her porch because her backyard flooded so badly that it reached her home where her porch was. Looking at benefits of, creek remediation or just improving water redirection, it benefits the community. It benefits the people who have their backyards, that are facing right up to the creek. Obviously that comes at a cost, which we discussed. But to me, that's the biggest benefit is helping the residents in preserving the historic significance of the region. I don't know if that's the answer you're looking for.
Sure, but there are values for that. So there you can put monetary values.
Like a monetary value.
Monetary values. That's
Okay.
why how you justify.
Okay.
So and there are and that's great. There's damage. There are damage functions that you can use. Obviously, we don't expect all of that to happen in the scope of this project, but you can relate depth of flooding to damage to the structure.
Okay.
right? That's one value that you can, that's preventive damage that can go in that estimate. There's another one, there are ecosystem values. You talk about, which is great, we talked a lot about wasteland creation. It has cultural value, it has climate regulation value, it has flood reduction value a little bit. All those have monetary values that you can put together and justify, and maybe fail to justify it.
Okay. Perhaps we can look into that.
Yeah, I definitely think, we didn't consider doing an actual like, number calculated analysis for the destruction of the area, but we just, that would be a great idea to show how much of an impact this would have.
Another question I had was about the growth rate used for traffic, future traffic. Yep. So what was that based on? Because I mean that has to factor in future population.
So we basically I used that, we looked at the historical data for the Aberdeen Gardens area, and from I think the year it was built, on average, that's how much it grew over the year, like over each year.
So can you speak to how much the growth was happening?
What was that?
Of how much growth was happening in the track?
Yeah, so over the span, I think it was like the 60s that neighborhood was built. With the table showed that over each year, like it would grow 5% each year. So I kind of just used that for our projected 10 years.
I think it would be benefit to account for more recent projections, because I read somewhere that population is dropping in some areas. So it might be an overestimate to account for that. So Norfolk and Hampton, maybe they're dropping not too much, but you're not going 5%
We
each
just
year.
wanted to be as conservative as possible.
Yeah.
Yeah, run the growth run functions for capacity design, not infrastructure expansion. So that is correct design based capacity. Because just like you are doing lots of BMP and kind of refocusing, redirecting without drastically altering the existing infrastructure. Same concept. TP, so-called run function rather. Okay.
Yeah, I'm sorry, can I ask one more question? So in the beginning of your presentation, you analyzed the high water level watershed analysis for distribution. Did you use this information? It looks to me you just use the design stone with the precipitation intensity.
The same question, you talked about the water level, and was that used at all in any of the models?
A lot of our, for our BMPs, a lot of our BMPs couldn't adjust to a change in water line. It's like the area or the constraints that we were dealing with, it was either going to work or it wasn't. So it was possibly considered in designs that we didn't even present to you today because they didn't work. But I'm sure we could have done more to make our designs more specific to the water level and the rainfall intensity.
It relates more to the method you use for calculating the hydrographs. So did the hydrographs account for any of the tailwater elevation or not?
Mainly the high water elevation we looked into. That was sort of the first thing we started with this project. As we continue to research on BMPs, we found that as we discussed, a lot of our options were constrained and we couldn't go with this. So.
Because I think Scott mentioned some of the areas are tidally influenced. So this vegetation considered may not, for freshwater may not translate to.
We did consider actually, yeah. I forget what the database we used, but it was for the Virginia tidal area. I forgot that word, Regency or something. And we were like crossing off things that wouldn't work for this specific area.
Yeah, we weren't able to go in and test the water for salinity per se, but because it didn't feed directly into the sea, we just used a chart for, I don't remember the name of the region, but it's semi-tidally influenced, and we chose plants based on that. So they should have some salinity tolerance.
Indigenous plant versus salinity group vegetations are two completely different categories. So you do need to pick up correctly. Majority of the BMP, the vegetation as well as such as light stocking and all that, primarily recommended for indigenous state plants, right? Instead of just pulling out whatever it is.
They were chosen from a already curated
Right,
list.
yes, we have a very well established list of the plants we can choose. However, indigenous that are necessarily satisfied, but if the sole fruit or resistant to salinity. So
Right.
those you need to kind of be careful about picking.
I believe there were different zones that were shown to us, and we did assume that the zone was correct. We didn't test the salinity of the water, but we tried to use the information base that the plants had to choose ones that would work for the specific region.
In zone means what kind of the are you referring to the USDA, the agricultural growth zone, or is it brackish or salinity gradient zone in coastal plain? But which zone are you referring?
The coastal plain, I believe, actually.
So it's a brackish transitional salinity, the range that you're referring. Okay. You are picking up plants from there. However, I noticed, some of the plants you listed in there, like Elungo nucifera, which is lotus, as well as cinnamon fir and all that. Those ones survive if they are inundated on the water even a day. And think about this, all the vegetation you are considering over there, they are basically the growth season plants. So during the winter time or dormant season, there is no vegetation available actually doing the job. Think about when we are bombarded with rainfall, flooding, hurricane from this area. Like fall, very early in spring, where there's no vegetation in that. So focus on mitigating bioretaining as well as all that with vegetation. And the biggest event we're going to take place during the growing season. So that's another thing you need to think about. What are the alternatives you should mix and match so that it will be continuously sustainable for the particular intended functionality? Does that make sense?
Yes.
Yeah, planting and growing, great, but that's the time that we don't have any problem.
I think we actually perfectly agree with you, because when trying to it was disappointing, at least for me, to find out that one of the only things that we could do, that we knew we could do, was the vegetation alterations. Everything else just wasn't working out, this or that. It wouldn't allow us
There is
to.
no business point. Okay, this is the picture of your project site. The particular Aberdeen Creek area is also having a big name for Lake Sabah. Dr. Sabah was former and the director of the Hampton Engineering Department. He has been doing so many retrofitting of the drainage, stormwater drainage system over there. And the primary problem is not necessarily sea level rise or land subsidence over there. It's just simply for drainage routing within the existing conveyance system. That's why they call that as Lake Sabah, right? So question becomes, all the wonderful alternatives like permeable pavement nowadays being used almost like cure all, but it's not, because if you are collecting water, you gotta go somewhere, and especially for structured DMP by previous pavement, where the water is supposed to go? It's supposed to go into existing conveyance system, which has fundamental intrinsic problem. Then exactly. So argument becomes the bigger context of the design approach is there any so-called likelihood that you can make first retrofitting or improvement in the existing conveyance system? And what would be the gain that you can improve from or beyond what you are having problem with, right? Then remaining the difference is the one you can augmenting it or addressing it by adding so-called buying time, not necessarily fixing it, buying time until conveyance system clears up, and those retained waterway will be sustained and continuous level drained into. So that it's a kind of sequence drainage strategy. Okay. So if you do not understand the so-called existing storm sewer capacity problem and just keep adding BMP, not necessarily a good strategy. So what I'm trying to say is whenever you are doing design, I mean, in terms of the element and what you're supposed to do and how you did it in your project, very good, very thorough and very tight. And you didn't unturn any stone in there. So everything has been right. But give a context to design that Polidori mentioned. What's the benefit of this? Engineering is all about either you are fixing existing problem or make it better. But it has to be translatable to calculable benefit. Without knowing the bigger context of the problem you are dealing with from the very beginning, in your case, for drainage and conveyances, right? Then whatever subsequent design elements sometimes would become weaker contribution to the benefit, even though by themselves are perfect and thorough and so, bigger context. How many of you been in the projects during the design phase? All of them?
Yeah.
Good. So time to time, I hear people saying, we did this great design, and it's a nearby local area. They built it in that design. Always, be sure, visit your projects.
Okay, go ahead, please. Yes.
I'm not going to bore you, so I'll just get into the point. I'm going to the video, right? Either Zed or Finon, the overall Aberdeen Creek watershed, the creek flow rate 2 year, 5 year, 25, all that magnitude of the creek flow rate is what 1,700 for 2 year storm.
700 or 7,000 for a 25-year storm.
7,000
for a 25-year storm.
What about 2 year?
Oh, it's like 3,000, 3,200.
Do you have the sense of the enormity of 3,000 CFS?
Yeah. I mean, this last thing, maybe like post cleanup, when there's no trash, and this is all that's going into Newmarket Creek.
No, what would you guess the flow rate in normal conditions? On the precipitation, not just normal dry weather. The water flowing right down there. What's the flow rate in? That's a huge body of water. Yeah. What might be approximately the range of the CFS?
Maybe less than what I got. Or more, maybe more. I'm not really familiar with like what it looks like, on top of my head.
Trying to bring up the magnitudinal recognition of the CFS. calculatable put into the equation? Yeah, I got the number. Yeah, that's one thing. Does that mean 1,700 CFS? That's a huge amount of water.
Yeah.
Elizabeth River, somewhere around 500 to 600,000 CFS, including the net flow rate over the tidal cycle. So 1,700 is somewhere around let's say 1,350, somewhere in there. But it's a huge amount of water coming from that side of the water. So you do need double check, and especially the final concentrations are similar for smaller delineation and larger or fine. That's another thing we need to make absolutely sure, because hydrograph is just live and die with final concentration and what the L sub C, the treble length to critical the distance. Yeah. And your contributing catchment watershed area is very well graded surface. Okay. So the time to pick as well as time of the concentration, there should be a good contrast depending on the size of the water. But you do have almost identical composition. So just double check. Right there. Donovan, let's say the swell in both sides of the median is actually quite a good idea, and especially modifying the grading toward median would definitely improve among all the considerations the way I see it. By the way, do you remember what kind of trees the median currently?
I do not know what kind of trees.
What type of the trees are in the median right here?
Were they crepe myrtles?
Crepe myrtle?
It was a mixture. It was a mixture. There wasn't consistent.
Just give me a couple so that people will get the idea. No, that's your engine. Once you are redirecting water in there, tree has to be the major redirecting the water, right? Right. Let's give or take the typical waterfall and crepe myrtle and all that. Those are relatively flood resistant. They can sustain. But there are also cypress as well as a number of different derivatives. If they are inundated, they stay under the water for days. Those trees will die. So think about redirecting toward the media is a great idea, but is it applicable corresponding to existing vegetation? And you guys all valuing existing vegetation. So making sure it will not going to harm the vegetation, still do the functionality. Yeah. One less thing that the so-called the litter trap that has become quite popular nowadays. But to be able to institute the litter trap, you first have to do the annual flow rate analysis for the creek.
So part of the catch with the litter trap is that the design that was most appropriate for our creek, it was a sort of all or nothing. They didn't give us the details about how to design it ourselves. They said, you just buy it from us and we'll design it. So I was like, okay, like I'll put it, in our plans. But they, it was difficult for me because
That's fine. I'm not deciding in that regard. Just to remember, any flow collection devices or implementation, if you are placing it in low flow condition body of water, they become clearer.
Yes, yeah, I understand.
So always start with annualize the water depth for analysis and take average and so-called minimum, maximum, and the worst case scenario. That's the one you can choose what capacity size and flow.
Using the information that we had, that's why I went with the design type. But I definitely would look more into that if I were to get, in more details on this.
You have something you like, but you have to put it in there. You completely disregarding what that is and only think of it. I think this should be good. It's not design.
Well, it wasn't completely it wasn't like uneducated guess.
I'm not criticizing you. Those are sometimes the pitfall. They think, oh, this will be artificial things, it's a slice of bread, will do the trick all that, and later on found out, yeah.
Yeah.
About the capacity of the trash cage.
Yeah. So yeah, we live a track.
How often is it? I think that we can fill up in a day. Right?
Well, it's one of, I chose it because it's one of the lowest annual maintenance. And it is also the
But somebody has to go and empty it.
yeah, and then that maintenance can be sponsored. And done, it can be done through like professional service and it paid for by sponsorship.
Who is sponsored?
The city.
City, that costs.
The people who the people who we would be getting the litter trap from essentially, through their consulting services, they would seek out the sponsorship for us. They would advise us on how to do the upkeep, the whole thing. It's set up so that like anybody can, purchase a litter trap for their creek or if they want it, it's tailored quite nicely to the school and its situation.
We tried to contact the city of Hampton on the trash problem. We faced a lot of issues with that. We were left on hold many times. It was just really hard to get in touch with people because at first we were considering no dumping signs. We thought that was a good idea, but we were told that the city of Hampton actually doesn't do that anymore because it actually attracts trash. People see the no dumping signs and then they dump trash. So that, but yeah, we contacted them about the trash trout. We wanted to kind of just propose it as a theoretical idea and see how that would work in conjunction with them, if they would, hire people to empty it out but
it can be a volunteer service, sort of like similar to, the Adopt a Spot program, but it can be something like that. It's just the logistics of that. We didn't get to go down that rabbit hole.
I'll just throw out that there is a group, I think there's a sorority that does a weekly trash cleanup at the school. And they could be tied in quite nicely.
At Aberdeen Elementary School. I was told that there's not any sort of existing thing like that. They said they haven't been active for years. So, but yeah, if they're currently doing that.
Yeah, I think they go,
that's great.
maybe it's once a month, but I can, if you'd like to add to your report, I can send you the information.
That'd be great.
Yeah, absolutely. And then also, just, with that creek, I feel like a lot of that litter is not necessarily being generated on site, but it's just kind of coming down from that lava. It's the north. So
Yeah.
this.